Alrighty, welcome back. Hopefully this one goes a little bit smoother than the last one. We are picking up on section 11.3, that's page 451. And we're going to be talking about the short run behavior now of polynomial functions. So last time we were talking about the long run behavior, and so if we take a look here, the long run behavior of a polynomial was determined by its leading term. However, polynomials with the same leading term and the same long run behavior have very different short run behaviors. So if we take a look at that first example in the book, they give us three different polynomials, right? F of x, g of x, and h of x. F of x, g of x, and h of x all have x to the 4 as a leading term. And so they're all going to resemble x to the 4 in the long run. Right, they're all going to look like x to the 4 in the long run. Right, but if we zoom in, we can see that they all have very different looking short run behaviors. Okay, and so that's what we're going to talk about today, is the short run behavior. So to figure this out, we're talking about zeros. Okay, that's really what this section is all about. So let's see if this works. So let's do this. We are now in 11.3 and we're talking about zeros, and we're talking about multiplicity. Of polynomial functions. Of polynomials. Okay. Here's the big thing about this section. Factoring. Okay? We're going to basically factor these polynomials. So if we take a look at example 2, investigate the short run behavior of the third degree polynomial u of x equals x cubed minus x squared minus 6x. Okay, let's do that. Example, u of x equals x cubed minus x squared minus 6x. First thing we're going to do is we're going to factor this. So check for a GCF. When we factor out of all these terms, we can factor an x out. It leaves me x squared minus x minus 6. That's a 6. There we go. Okay. Now continue factoring. We're going to factor this completely. So x squared minus x minus 6 can be factored further. This would be now sum product factoring. Ooh, that was pretty bad. So we have our x out front still, but what is this going to factor into? What numbers multiply to negative 6 and add to make negative 1? Negative 3 and positive 2. So we get x minus 3 and x plus 2 as our factors. And we're finding zeros here. So if you remember with quadratic functions or back from A2 polynomials as well, we would just set this equal to 0 and solve each one. However, what's going to be important is to remember the connection between the factored form and the 0, right? So this single x will give me x equals 0 as a solution. X minus 3 as a factor gives me x equals positive 3 as a 0. And x plus 2 gives me x equals negative 2 as a solution, okay? And so there are our zeros, Okay, now if we go ahead and we take a look at what this might look like, well, its leading term is x cubed. So we know that in the long run, it's going to do this, and it's going to do this. Right? That's the long run behavior of it. Excuse me. Now we also know that there's a 0 at x equals -2. Maybe that's like right here. We know there's a 0 at 0. And we know that there's a 0 at 3. Right? And so now I could just kind of like fill in and sketch what this might look like. Kind of mess that up a little bit, but we know the general shape of cubic functions, so we can kind of fill that in. We get something like that. So now we can kind of identify where the function's positive, right, in between there and everything after that, where the function's negative, in between there, everything before -2, and so on. Okay? That's short run behavior in a nutshell, right? So let's go back. There's our example 2. Let's take a look at the number of factors, zeros, and turning points. This might sound very familiar to you. So what is the maximum number of zeros of a polynomial? Well, if you guys remember, if the degree is, say, a degree 5 polynomial, then let me just kind of show you to you an example. If we're talking about a degree 5, then we could have sort of 5 linear factors, right? So we could have like x plus, I'm just going to start making up numbers, x plus 1, x minus 7, x plus 8, x minus 4, and x minus 3. Okay, so this is a degree 5 in factored form because it's all 5 different linear factors. And so we can see that, you know, if I added one more factor in here, well, now it's going to be a degree 6, right? And so it kind of determines on how many linear factors you can have. And so that's why the maximum number of zeros for a polynomial is the same as its degree number. So any polynomial of degree n, right? So any number, so degree 7 has at most, can have fewer, and we'll talk about that in a second, can have at most n zeros. Kind of ran out of room there. N zeros, right? So for example, degree 5 has at most 5 zeros, degree 7 has at most 7 zeros, degree 24 has at most 24 zeros, and so on. Okay? How about turning points? Well, let's actually go back to this example. We had a degree 3, and take a look at the turning points. There's one here, and there's one down there. So there's 2 turning points on a degree 3. And so the idea here is that any polynomial of degree n has at most n minus 1 turning points. So, for example, a degree 8 polynomial would have at most 7 turning points. Okay? Now, how could we have fewer? Well, we have something called multiple zeros, which I call multiplicity, right? So if we take a look at this here, in the function s of x equals x minus 4 squared and t of x equals x plus 1 cubed, they're both polynomials and they're both in factored form. If we write this out in expanded form, this is kind of what I want to point out to you guys here. Let me just, there we go. Right, so if we write this out, not fully in expanded form, but if we just kind of expand the exponent, x minus 4 squared is x minus 4 times x minus 4, right? So if I were to solve for the zeros there, well, I'm going to have x minus 4 times x minus 4, and so I'm going to get x equals 4 and x equals 4, right? I get two zeros at x equals 4. We know that we don't have to write x equals 4 and x equals 4 because it's just 4, right? That's all there is to it. Anyways, that's what we're talking about here. So if we're talking about like x plus 1 cubed, right, that expanded would give us x equals negative 1, but it would happen 3 times. That should say times. That doesn't look like it at all. 3 times, okay? So that's what we mean about multiple zeros or multiplicity. And what happens is we get a little bit different behavior in the graph when that happens, because as we know, even though the 0 is at negative 1, this function x plus 1 cubed is not the same as just x plus 1, right? It's very different. And so the multiplicity affects kind of what happens really close to that 0, what kind of what happens of how it approaches that 0 value. So let me bring that up. So we're talking about the multiple zeros, and just kind of summarize this, okay? This will be kind of like our summary here for multiple zeros, multiplicity. If there is a single 0,
I didn't get that.
all right, very nice. If there is a single 0, then the function itself, the function crosses the x-axis kind of normally, right? Just goes through, okay? If there is an even number of multiple zeros, so if there's an even number of multiple zeros, what that's going to do is that's going to, what the book says, bounce off, right? It says bounce off, but we usually call that a touch and turn, right? So touches and turns. At the x-axis. And if there is an odd multiple zeros, then it's going to cross the x-axis, but it's going to cross with inflection. There should be an N somewhere there. Inflection. okay? And so, quick examples of these, a single zero would just cross. A multiple zero would touch and turn. Yeah, I got put some arrows there. Nice. And odd multiple zeros, what's going to happen is it's going to cross, but with inflection. So it's going to kind of flatten out here and then kind of change concavity. So if you remember back to when we were talking about concavity, an inflection point is where that concavity changes. So it kind of flattens out, does one of those little swivels. Okay? So let's take a look at example 4. So this is really the main part of this section here. Putting all this together, knowing the connection between zeros and factored form, we can now kind of look at a graph and write a possible polynomial function. So let's take a look at example 4. Find a possible formula for the polynomial function graphed. You can't see it. There it is. So, what do we see? What do we see here? I see a 0 at -1. I see a 0 at +3. And I see a y-intercept of -3. So, actually, you know what? Before I even go into this, let's quickly talk about factored form. Because there's a very important part of a factored form. So if we have a function f of x in factored form, it's going to be a leading coefficient a, and that's the important part, and then all of your little different factors, so like x minus r, x minus s, right? That's actually what we use for quadratic functions. If I stopped there, we would have a quadratic function. This is quadratic. So for a polynomial, what that means is we can just keep adding those linear factors on and on and on. So f of x equals a times, let's do like x minus x sub 0, x minus x sub 1, x minus x sub 2, and so on, okay? Okay, and that would be for a polynomial function. So now using this idea, let's take a look at that graph in example 4. So this is f, so f of x equals, start with your a, and then start writing your zeros. So I notice the 0 at -1 just crosses normally. So I'm going to put x plus 1, right? Because if the 0 is at -1, my factor is x plus 1. My other 0 is +3, so that's going to be x minus 3. But what do we notice about that 0? It touches and turns. So we know that it has to have an even multiplicity. And so technically speaking, we don't know if it's an exponent of 2, 4, 6, 8, or so on. That's why the question says find possible formula. So we're just going to do 2 because Why not? Okay, but it's got to be an even one. So there's the information we have. Okay. Now we know what the y-intercept is. The y-intercept is -3. And remember, a y-intercept means that the coordinate point is 0, -3. So when I put 0 in for the x's, I output -3. So now I'm going to just plug that information in. And now I can solve for my a value. So what I did there was, remember, I plugged 0 in for x, and I plugged -3 in for my output. Okay? And so now I get, well, that's going to be -3 squared is 9 times 1. Let me just show you that. So let's just simplify this. Let's do all of that. It's going to be 9 times 1 is 9, so we got 9a, divide by 9, and we get, what is that? -1/3. And so now we write f of x. Don't forget this last part. Like, don't just stop after finding a. Make sure you write the actual function. So -1/3. That's a 3. X plus 1, x minus 3 squared. Okay. And the book as well kind of walks through that process. All right? And that's it for 11.3. So again, we got a couple of practice problems to work on. And again, let me know if you have any questions. Drop by the office hours if you want. And hope you guys are doing well. All right. See you later.